Have you ever really stopped to think about what's going on under the hood when you run a piece of code? It feels like magic, but it's not. It's actually more like this secret, bustling city humming with activity right inside your computer. So today, we're going to take a tour of that city and uncover some of its biggest secrets. Let's dive in. All right, to get things started, I've got a question for you that might just kind of flip what you think you know about computers completely on its head. Do you really need an operating system? Like, do you need Windows or Mac OS or Linux to actually execute a program? Just think about that for a second.
The answer is a short, simple, and honestly, pretty mind-blowing. No, you don't. It is absolutely possible to write code that talks directly to the computer's hardware with nothing, and I mean nothing, getting in the way.
So, what in the world does that even look like? Well, there's a name for this. It's called programming on bare metal. It's just your code and the raw, untamed power of the machine. And for some really specific, high-stakes situations, this is the absolute best way to do things. We are talking about blistering speed with ultra-low latency, squeezing every last ounce of performance from the hardware and having total, complete control over everything. There's zero OS overhead. This is absolutely critical for things like high-frequency trading, where every single microsecond is worth money, or for tiny little embedded systems, like the chip that runs your microwave. And trust me, this is a gigantic but. There is a very, very good reason we don't all do this. It is unbelievably, profoundly difficult. I mean, trying to program on bare metal for just a normal app would be like trying to build a car from scratch, nut by bolt, every single time you wanted to drive to the store. And that right there brings us to the unsung hero of this whole story, the operating system. See, it's not a strict requirement for running code, but it is, without a doubt, our most powerful and indispensable helper. Just imagine this for a second. Without an OS, you would be the one telling the graphics card how to draw every single pixel on the screen right now. You'd have to personally manage every byte of memory like a super careful librarian for billions of tiny little slots. You'd have to write the code for your mouse and keyboard from the ground up. It is a logistical nightmare, and that is exactly why we have operating systems. So here's the bottom line. Operating systems are the ultimate convenience layer. They handle all the messy, tedious, and mind-bendingly complex work for us so that we can focus on the fun part, actually building our applications. It's a helper we should all be pretty thankful for. Okay, so now that we have a healthy appreciation for our helper, how does the OS actually manage our programs? Well, it wraps every single one of them up in this neat little package called a process. Every app you open, every command you type in the terminal, it becomes a process. So our mission now is to carefully dissect one of these processes and see exactly what makes it tick. And really, the best way to understand a process is by taking a guided tour of how it's laid out in your computer's memory. This internal structure, it's like the blueprint that controls everything about how your program runs. Let's break this down. Just think of a process's memory space like a building. Down on the ground floor, at the very bottom, we have the text or code section. This is where the actual instructions for your program live. Right above that, we have the data section, which is kind of like a permanent storage room. And then here in the middle, we have these two really interesting sections that actually grow towards each other. The heap, which grows up, and the stack, which grows down, leaving free space in between. So let's take a closer look at each one of these floors. The ground floor, that text section, is the foundation of everything. It contains the raw machine code, the ones and zeros, the MOV and add instructions that your CPU understands directly. And this part is read-only for a super important reason. You do not want your program accidentally rewriting its own instructions while it's running. That would be total chaos. Okay, moving up a floor, we find the data section. Think of this as the building's long-term storage vault. This is where any global or static variables are kept, any piece of information that needs to stick around for the entire time the program is running. Next up is the heap. This is the flexible, dynamic part of our memory building. It's for things you don't know you'll need until the program is already running, like, say, a list of users that grows as more people sign up. Whenever your code asks for more memory on the fly, this is where it comes from. It grows upward from the bottom, but it comes with a big responsibility. In some languages, you have to manually give back what you take. If you don't, you'll cause what's called a memory leak. And growing down from the top, we have the stack. The stack is the ultimate short-term organizer.
Every single time your code calls a function, a new frame gets placed on the stack. This frame holds all of that function's local variables, and it remembers where to go back to when the function is done. It is incredibly fast, but it's also limited. That's why if you have a function that calls itself way too many times, you get that infamous Stack Overflow error. The stack literally ran out of room.
And this is just a brilliant way to picture how it works. The stack is just like a stack of plates at a buffet. The last plate you put on top is the first one you're going to take off. Last in, first out, or LIFO. When a function finishes, its plate is taken right off the top, and we're right back where we were in the function that called it. It's simple, it's fast, and it's really elegant. So here is the crucial trade-off, and it's why understanding all this helps you write better code. The stack is blazing fast, and it's all managed automatically for you, but it's small and it's rigid. The heap, on the other hand, is huge and flexible, perfect for data when you don't know the size beforehand, but it's slower and it requires much more careful management. Just knowing where your data lives can help you avoid bugs and write way more efficient programs. Okay, so now that we've toured the entire memory building and we understand the anatomy of a process, we have all the clues we need to solve a very, very common mystery in the programming world. And the mystery is this: why are these hugely popular languages like Python or JavaScript generally considered slower than a language like C? The secret, it turns out, isn't really in the languages themselves, it's in how they run. And the answer is hiding inside that process model we just learned about. So a C program takes a very direct path. You write your code, a compiler translates the entire program into raw machine code all at once, and you get an executable file. When you run it, the OS creates a process, loads that machine code right into the text section, and the CPU just gets to work executing it directly. It's a straight shot, super efficient.
Now, let's compare that with Python. When you run a Python script, you aren't actually running your script directly. You're running a different program called the Python interpreter. And get this, that interpreter is usually a compiled C program itself. So this interpreter program starts its own process, then it reads your Python script line by line, figures out what you're trying to do, and translates it into machine instructions on the fly for the CPU to execute.
And there it is. That's the solution to the mystery. You're not just running one program. You're really running two. The interpreter program, which is then running your script. That extra layer of translation, that middleman doing all the work at runtime instead of beforehand, that is the overhead. That's where the performance difference comes from. And once you really see all this, the process being created, the memory layout with the stack and the heap, the different layers of execution, you start to appreciate the incredible complexity that's hiding behind even just a single line of code. It's a truly amazing system when you think about it. So now you've seen it, the hidden, the complex, and the deeply fascinating life of a program. You now know about the secret city inside your computer, and it kind of makes you wonder, doesn't it? What other invisible worlds are humming away inside our machines, just waiting for us to explore them?